In our last session, we ran a packet loss test for the first time. Now we're going to use the packet loss test to gather some data from the card so we can analyze with Wireshark what's going on over the wireless interface. So packet loss test, we have already set up the ports. We set up the clients. This has not changed from our earlier sessions. And we're going to do just a 2-second packet capture, very, very short. Actually, we can even make it shorter, a 1-second packet capture. You'll find when we're running 80,000 packets a second that you can fill the memory in the cards, 256 meg, pretty quickly. So we're just going to run 15 18-byte frames. We'll run 90,000 packets per second. We're going to put the device under stress. And we've chosen to run Ethernet to wireless. Now on the port card, if you remember in an earlier session, this is where we can instruct whether the hardware log is to be included in a download or not when we select the option, Save Hardware Logs After Test. So we want the Wi-Fi log, but we really don't need the Ethernet one, so we've unchecked hardware log in the download. So this will give us the log file from the Wi-Fi card as a result of running the packet loss test. 15 18-byte frames, 90,000 packets a second, Ethernet to wireless. Okay, so we'll press the green button, and we see that the very same thing happens that happened before, which is just run through and set up the clients, connect them, ARP through, and begin running the traffic. Now, it doesn't run for very long. Now, what we'll also see, so we got 987 megabits downstream. There was 0 frame loss, right? So this is this access point has actually got gigabit capability on the Wi-Fi side and the Ethernet side. So we're maxing out the offered load on the Ethernet side as well. Now notice that it is telling us what file folder things are being stored to. So in this case, we can go to that file folder. Okay, it's done doing that. So we can highlight that file folder, which we'll do. We'll copy it. We'll go to Documents, paste it in, and there we have a results directory. Now, one of the things that I'm introducing here is the concept of this results directory. Every time an application runs a test, it creates a separate file folder in the results directory that is time-stamped. In there will be the console view, right? This is what was displaying at the bottom of the page. So you can see if you need to go back and see, hey, what was going on as the test went ahead and ran. There's the console view, the detailed data for the packet loss test. So you can highlight those, spread it out, and here's all the data that's stored. There are results from RSSI and the packet loss test that we just ran. There's a time log, and this is the transcript of commands that were sent from the application to the chassis and what came back, so that can be helpful in diagnosing problems. This is an important file here. This is the config file. So every time a test is run, the configuration of the application is stored in a config file. So you can go back and run it again. It happens every time you run a test. But this is the file we're going to take a look at here. It's a .vwr is the type of file, and it is a capture file. So this is all of the packets that are sent or received at the front panel of a Wi-Fi card or an Ethernet card, for that matter, is stored in memory. So we'll open it up here using Wireshark. Now we're using the Wireshark that is supplied by Ixia, so it has the VariWave dissectors. What we can now watch is the process of the card connecting up. It's we can see the beacons coming in here. We can see our card probing. So everything that is -6, for example, that's what we set our transmit power to, remember? And so we can see the authentication, the association, the DHCP AMP process going on. We see the gratuitous ARPs that we had selected. These are learning frames, so we send a few frames out to make sure that the frames can get from one end to the other, and the device under test has the routing path set up. And then there'll be a little bit of a delay. Then here's where we begin running traffic very quickly. Now, we can diagnose a little bit of what's going on here by taking a look at the columns. Notice the columns I have are time, just the time from the beginning of the test, whether the frame received was FCS errored or not, the phi rate, the MCS index, the interframe gap, this one is very important, RSSI, the VariWave sequence number that we put in each packet that is generated, client ID, the WLAN sequence number, that this would be the WLAN sequence number that the access point would have assigned, and then you've got source destination, right? So what we're seeing here is an AMPDU, right? But notice that the WLAN sequence number is repeated on successive frames that we created. So this is a 1518 byte frame. If we look at its length, its MSDU length is 1538. So we started out with a 1518 byte frame. This access point is taking two of those frames created on the Ethernet side and making an AMSDU out of them. And then each pair, each AMSDU is then becoming an AMPDU. So this is an AMPDU made up of AMSDUs. And so we can see the individual frames, we can see what the WLAN sequence numbers are, and we can tell that by looking down into the radio tap header information. Notice it says an MPDU, first AMPDU, last MPDU, etc. This tells us logically what's going on here. So we can see this is the first MSDU of an AMSDU, and this will show up as the last MSDU of an AMSDU. It'll also be the first MPDU of an AMPDU. And then this will also be the first MSDU of an AMSDU. Sorry, I went past it here. First, and it's not the first MPDU any longer. So this is AMSDUs being made into AMPDUs, and away we go. Now, the other thing that's important to look at here is interframe gap. This AMPDU is being sent, and here's a block ACK. This block ACK is happening at 16 microseconds, which is minimum interframe spacing. And we can go down to the bottom and see what the starting sequence number was and what the block ACK bitmap is. Well, since this is the beginning of your AMPDUs, there's going to be apparently a lot of frames missing, but they really aren't. The frames that are missing are the frames that have not come through yet. Okay, but we also see that the next AMPDU that's being sent by the access point happens at minimum interframe spacing, 17 microseconds. These numbers in between here, this large interframe gap, you can ignore that. It's a Wireshark issue. Basically, what you're looking for is the interframe gap to the start of the AMPDU, and then you'll move on to the interframe gap to the block ACK. So we see here that every time the access point goes to send another set of data, it's doing it without randomly backing off. It's sending it out at minimum interframe spacing. Here we are again. Here we are again. Here we are again. Each one of these should have random backoff occurring. If we go far enough down here, we'll see that there is random backoff that the access point uses on a request to send. But let's analyze that just a little bit here. So this request to send, if we go to the bottom here, is asking for 714 microseconds. The clear to send subtracts the duration of the last frame and says, sure, you can have the next 670 microseconds available on the air. So the next thing that gets transmitted, that starts that 670 microseconds. Let's right click here and set a time reference. So this becomes 0 time. So let's see what happens 670 microseconds later. This AMPDU is sent through the air. The ACK occurs, right? And here comes the next AMPDU. So at 676 microseconds, the access point does not perform random backoff, but sends another AMPDU directly following the block ACK. This is illegal. This is typical with 802.11ac, but it's not legal. So what's happening is this access point asked for 670 microseconds. It got it, but then rather than asking again using random backoff before the RTS to ask for another period of time, it simply is continuing to send things into the air beyond which the CTS granted it. Let's go further down here and see what happens. So here we are 1.3 milliseconds, and it jumps on the air again immediately. It jumps on the air again immediately again 2 milliseconds later. Here we'll keep going, we'll keep going. Eventually, we hope, here we go. Here's another request to send coming from the access point, right? And we can tell that because this is a received frame. Notice here it says received. So nearly 5 milliseconds later, so 4.9 milliseconds later, the access point sends another request to send. So it had been granted the media for 600-ish milliseconds. It sent an AMPDU, but it continued to send frames at minimum interframe spacing for 5 milliseconds, which would not allow any other device within earshot to get a word in edgewise. This product clearly does not meet spec. Now, what we're going to see when we get to a throughput test, that this Netgear access point does not meet spec, because you'll see that the throughput in the downstream direction exceeds theoretical max, and this is why. But once you ran a throughput test and saw that it exceeded theoretical max, a very good way for you to diagnose it is what I've just shown you here. Take the same setup that you're running, go to a frame loss test, set the frame loss test for a very short duration, because all you're looking for is a bunch of data where the device is doing whatever it is you want to see, but without filling up the log file. So 1 second, 2 seconds worth of data can be plenty. You can go to the advanced test parameters and shut off the report if you don't want to see that. You go into the option page, save the hardware logs. Remember to choose which cards are going to provide the hardware logs. And then in that results directory, you end up with the VWR log file. Open that up, and there's all the proof that you need of what's going on over that Wi-Fi interface. So this is running your first packet loss test to do packet analysis using Wireshark. And in our next session, we will open up the applications and start looking at throughput.